Alright, let's consider another example where we're gonna do some design with the root locus technique. So consider the system, our standard feedback loop with a controller over here, GC of S, and the plant function is equal to 10 over S times S plus 1 times S plus 6. And we have the unity feedback over here. And we would like to design a PD controller. So we'd like to design a PD controller such that the closed-loop system has dominant poles with psi equals square root of 2 over 2 and omega d equals 1 radians per second. And so what we would like to do is to find the coefficients of a PD controller. So let's start writing down the coefficients of a PD controller, right? So it has the standard transfer function of form k plus kds, p term and a derivative term. And we want the closed poles to be dominant at the locations. We can write down the desired pole location as well, because in a underdamped response, pole locations are, as you already know, is minus psi omega n plus minus j omega n square root of 1 minus psi square. This is also equal to omega d, right? So this is omega d. And this is also given as 1, and psi is cos theta, and cos theta is square root of 2 over 2, so theta is 45 degrees. So omega d is equal to psi omega n, and this is equal to 1. So this is omega d and equal to 1. So that root is simply equal to minus 1 plus minus j. So those should be the closed pole locations when we add our controller and specify the k and kd values. So we're gonna solve this problem in 3 different ways. So I will start from solution 1. So solution number 1, let's say. So in this approach, what we will do is to focus on the characteristic equation of the system. So I will write the transfer function as g closed loop of s is equal to 10 times k plus kds divided by s times s plus 1 times s plus 6 plus k plus kds. So we're going to focus on the denominator of the closed transfer function, and we want the dominant poles to be at -1 plus j. So we can do it quite simply, I should say. So I will write this as equals as, say, m bar of s divided by d bar of s. Okay, and I will focus on the roots of d bar of s. So let's focus on that. So d bar of s is equal to, what is it, s cubed plus 7s squared plus 6s plus kds. So it is kd plus 6s plus k. And we want that d bar has roots -1 plus minus j. Okay. So what we can do is that we can write d bar of s and evaluate it at s is equal to -1 plus minus j, but I will pick plus j for the time being, and equate it to 0. And from there, I'm going to have the imaginary part to be equal to 0 and the real part to be equal to 0. Then I can find two unknowns, two equations. So let's try to do that. So I will delete this guy over here and write this thing explicitly. So I will have -1 plus j cube plus 7 times -1 plus j squared plus kd plus 6 times -1 plus j and plus k equals 0. By the way, I just noticed that there's this 10 term over here, so I'll have those 10k and 10kds over here. So this is 10k plus 10kds. Therefore, there will be 10kd over here as well. $10kd, and this is also 10k. I think we are good to go if we continue this way. Just some. So it's KD. All right, so that will be equal to 2 plus 2j plus 7 times minus 2j plus 10kd plus 6 times -1 plus j and plus 10k equals 0. So let's write down the real part and then the imaginary part and equate them to 0. So if we have a look at the real part, so there's 2 here. What else? I will have minus 10kd minus 6 and plus 10k equals 0. So I do have from there 10 times k minus kd is equal to simply 4, right? Okay, so that's the first equation. Okay, and from the imaginary part, I will have 2 here minus 14j, what else, and j, so it's going to be plus 10 kd plus 6 is equals 0. And from there, what I have 10 kd is equal to, so it's going to be 12, 6, right? So it is 6. So kd is 0.6, 0.6, and 10kd is equal to 6. Then 10k is equal to 6 plus 4 equals to 10. Then k is equal to 1 over here. And from both of them, k is equal to 1, kd is equal to 0.6. So our controller is simply equal to k plus kds, and that will be equal to 1 plus 0.6s. So let's solve the same thing with the polynomial division this time. Okay. So, oops. So solution number 2, something like this, so that I do have the characteristic polynomial, and I want minus 1 plus minus j to be root of the characteristic polynomial, right? So d bar s is the characteristic polynomial, and I want minus 1 plus j plus minus j to be the root of this polynomial. So what I can do is a polynomial division, right? So I can first construct the second order polynomial which has the roots minus 1 plus minus j, right? So I can simply write obtained polynomial s plus 1 minus j and s plus 1 plus j. That would be simply equal to s plus 1 squared plus 1. So that is equal to s squared plus 2s plus 2. Okay. And next thing is that I know d bar of s should have roots over here, so I can make a polynomial division. So let me do that. So I will get d bar is s cubed plus 7s squared plus 10kd plus 6 s plus 10k divided by s squared plus 2s plus 2. Okay. So I will first multiply this guy by s so that I will have s cubed plus 2s squared plus 2s and subtract this. So I will end up with 5s squared, and that will be simply equal to plus 10 kd plus 4s, plus 4s plus 10k, right? So the next one is going to be s plus 5, so I will end up with 5s squared. So I will have 5s squared plus 10s plus 10. If I subtract that thing, I will have a remainder which will be equal to 0. Okay, and that simply states that 10 kd minus 6s plus 10k minus 10 is the remainder, and that should be equal to 0. And so this is equal to 0, so k is equal to 1, and this is equal to 0, then kd is equal to 0.6, and from there, once again, gc of s is equal to k plus kds, so it's equal to 1 plus 0.6s. Okay, so that was quite straightforward and doable, and we will continue with the graphical design. So solution number 3. Right, solution number 3. So that will be slightly different than the first two approaches over here. Okay, so I will start to use the root locus itself and try to use the angle and magnitude condition. So once again, I will write first the controller transfer function, which was equal to k plus kds, and I can write this thing as taking kd out as s plus k over kd. Okay, and I will call this guy, this variable over here, as alpha. Let this be alpha. So this will be simply equal to kd times s plus alpha. So good news is that now I do have a controller which has a free parameter kd and a 0 location in the open loop transfer function that I can determine the 0 location, right? So you can do it by inspecting the root locus and decide where these alpha should be if this s has to be included, the desired pole locations are included in the root locus. So let me draw an S-plane first. So let's try to do something like this, okay? So this is our S-plane. And let's have a look at the open loop transfer function. So our open loop transfer function is going to be 1 kd times s plus alpha. So 1, 0 that I can put at minus alpha. And there are 3 poles at 0, minus 1, and minus 6. So let me put those pole locations. So 0, minus 1, and minus 6 over there. Okay. Good. So, and there's a desired pole location which was given as minus 1 plus minus j. So at this point over here, I have the desired pole locations. Okay. This is minus j. Okay. So I want the root locus to pass through that point. Okay. And there will be an alpha which I will put on the real axis. So, but I don't want to put it on the right half plane. There should be somewhere on the left half plane. I don't know its position yet, but I will put it somewhere over here for the time being. Okay. I will put it with a empty circle over here. Okay. So if a point on the root locus is included, if a point on the S-plane is included in the root locus, then it should satisfy two conditions, angle condition and the magnitude condition. So let's try to write down the angle condition for this guy over here, okay? So I will try to plot those vectors. So this is the S plus alpha. And I'm going to inspect those angles, right? Good. And I will call these angles as, for example, let this guy be theta 1. Let this guy be theta 2. By the way, that's 90 degrees, right? Theta 2. And this be the S minus alpha, so it's going to be, let's say this guy psi. And let this be theta 3. Okay. And I should also maybe explicitly write down this is equal to minus alpha point over here. So we have the term S plus alpha in our control in the Occlum transfer function. So that will appear as a minus alpha 0 over there. And it's unknown at an unknown location. We don't know what it is yet, where it is yet. So let's first try to write down the angle condition. So angle condition. So the angle condition is going to dictate us that. So angle of S plus alpha minus angle of S minus angle of S plus 1 minus angle of S plus 6 should be an odd multiple of pi, right? So 2k. So it is 2k plus 1 times pi. So I will call this angle as S minus alpha, it's the angle of S plus 1, so this vector over here as psi. Then the angle with the S is S minus 0, so this angle of the S vector over here is theta 1, minus S plus 1 is S minus 1, theta 2, and theta 3 is equal to 2k plus 1 times pi. So let's try to write them down. So then psi minus theta 1 is equal to 3 pi over 4. So this is because the point minus 1 to 1. That's the 45 degrees. And minus pi over 2. And theta 3 is equal to, so notice that the length of this thing is 1 and the length of that thing is 5. So theta 3 is minus arctangent 1 over 5. Should be an odd multiple of pi, let's say, for example, minus pi. Okay, so you can put that. And arctangent 1 over pi is something like this, so it will be around 11.3 degrees. And if you do the computations, then you will see that psi is equal to, I'll write it over here, and from there, psi is equal to 56.3 degrees, okay? So that's a 56 degree over there, okay? And by the way, from the tangent of that thing, you can find alpha, right? Because as you see over here, the tangent of psi is equal to 1 over alpha minus 1. So I write it over here. So tangent of psi is equal to 1 over alpha minus 1. And apparently tangent of 56.3 is something like 1.5. And from there, alpha is equal to 1.67 approximately. So from there, alpha is approximately 1.67. Then the next thing is to do is to write down the magnitude condition and find the corresponding KD value. Okay, so let me write it over here. So now I found alpha, which was equal to K over KD, and I should also find the KD value as well. So if I write down the magnitude condition over here, maybe, so the magnitude condition dictates that 10 times KD times then the magnitude of the S minus alpha is equal to square root of, since alpha is 1.67, so this length is 0.67 and this length is equal to 1, so it's going to be 0.67 square plus 1 square, which is equal to 1, and divided by the length of those vectors. So one of them is equal to 1 over here, s minus 1. The other one is simply equal to square root of 2 over here, right? So 1 times square root of 2 times square root of the length of this vector is equal to 5 square plus 1 square. So it is going to be 5 square plus 1. This should be equal to 1 from the magnitude condition. And from there, KD will be equal to square root of 26 times square root of 2 divided by 10 times square root of 1.45. And if you carry out these calculations, it's approximately equal to 0.6 there. Remember that we define alpha as K over KD, so let me write it over here. So that is equal to K over KD is equal to 1.67, and we found KD to be equal to 0.6. So if you combine those together, then K is approximately 1 and KD is approximately equal to 0.6. So we found our controller to be equal to K plus KDS, and which is equal to 1 plus 0.6s once again by using magnitude and angle conditions and the graphical design. So I should also say that in the exams you should be comfortable with all these 3 solutions in case you need to use them. Okay, so thank you very much.